The integration of sine and cosine is quite straightforward if you're already comfortable with the derivative of sine and cosine. So the way I remember it is using the diagram of the derivative of sine and cosine. So we know that sine, the derivative gives you cosine, and we know, this is straightforward word, sine, the derivative gives you cosine, and the derivative of cosine gives you negative sine. The derivative of negative sine will give you a negative cosine if you take the negative as a constant, and then the derivative of cosine will get you back to sine. All of them in terms of x. Remember, with trigonometry we deal with radians. Now this is for the derivative. So let's say this is for derivative. Well, integration is basically antiderivative. So what you're doing is just going backwards. So you would say that the integration of sine is negative cosine, the integration of cosine is negative sine, the integration of negative sine is cos, and the integration of cos is sine. So you would take this as integration. So this diagram is quite helpful. It's good to write the derivatives and then reverse it in order to know the integration. So I'll go through a couple examples in this video, and then hopefully you're set for the derivatives of sine and cosine. Mainly we usually like to use the substitution method for sine and cosine, but at some point the integrations do become complex that you will have to end up using your calculator to solve them. So if I have something as simple as this, take a few minutes to solve it on your own. It's a definite integral. The first thing you could do is take the 3 out if you want to, and then integrate it separately. So if I take the 3 out, I'm going to end up with the integral from 0 to pi over 6. 3 is out, and all I'm left with is sine x dx. And if I go back to the previous slide, the integration of sine x is negative cos x. So I can integrate that, and it's going to give me negative cos x. I can multiply the 3 back in, or I can keep it out. I need to evaluate this integral from 0 to pi over 6. So I'm going to substitute pi over 6 first, minus the 0. Make sure that you're careful with the negative. This negative has to be next to the negative 3. And this negative is just because you're subtracting the 2 values. And then you simplify it and you end up with this. Now, if it was a non-calculator paper, you can actually keep it as this, because you need to remember what pi over 6 and what cos pi over 6 and what cos x is, using the exact values of trig. If you know the exact values of trigonometry, you would know that cos pi over 6, which is basically 30 degrees, is root 3 over 2, and that cos of 0 is just equal to 1, okay, which is why we get plus negative and negative, we get the plus, and the 3 goes in there. So if it was a non-GDC or non-calculator, then you can leave it as a fraction. If it was, then you just write the final value in there. Let's do a bit more of a complex question. What if I have the integral of this, which is a big load of mass? Things are being multiplied, cosine and sine, and so on. Now here's the trick. Every time you see cosine and sine being multiplied together, you can use the substitution method. Now there is another method using the trig identities of the Pythagorean trigonometric identity, if you want to, where everything then converts to a cosine. But then also, again, you'll have to use a substitution method or the reverse chain rule. So this is more advanced. So let's just use the chain rule here. Things will nicely cancel out, and it's a matter of practice until you get to see the pattern. So the first thing you want to do is substitute something that's quite complex, which in this case is sine. So I'm going to use u for sine of x, not sine squared, because if I do that, things won't cancel out later. You can try it, which is something I've done. I've tried it with u squared first, and things didn't work out nicely, so I just converted it to u equals to sine x. So once I have u equals to sine x, then you need to remember that you have to find the derivative of that du by dx, which is cos x. We know the derivative of sine x is cos x. And then you want to make dx the subject. So now what we've done is we've created a substitution for this and for the dx. Now, there's one additional thing, which is basically what we've done before normally, but there's one additional thing which we haven't dealt with, which are the limits. Because by definition, the limits go x1, x2, f of x, t of x, which is all nice. You then find the integral, the antiderivative, let's say this is the antiderivative, and you evaluate it from x1 to x2, and you're like, okay, that's nice, I'll just substitute it in there. But what we're going to do now is we're going to replace the sine x and the dx with du and x and u, replacing them in there. But my limits will still remain as x, and I won't be able to substitute them in there because my limits are x and my function is u. So it's contradicting. So what we do actually is we change the limits as well, which is not something complex. You either do it now or you do it later, or maybe you don't want to do it, that's fine, but I'm going to explain how to overcome that. But we usually, when you're doing by substitution, you stop here if your integration is a indefinite integral. But because we have definite integral, meaning you have limits in here, you have to change the limits. Now, how do you do that? Basically, my limits are in terms of x, but I want them in terms of u. Well, I know what u is. U is basically sine of x. So all I'm going to do is I'm going to substitute my integrals, my limits in there in order to get the limits in terms of u. So this is what we're going to get. So this is the upper limit. If you notice, I'm just substituting pi over 2, which was the upper limit, into sine of x, and I'm getting 1. So now instead of pi over 2, I'm going to put in 1. And for the lower limit, I have pi over 4, and I'm going to substitute it in sine. And instead of pi over 4, I'm going to get 1 over root 2 or root 2 over 2. These two are equivalent. It's a good fact to remember. So now we're going to put everything in. We have our u, we have our dx, and we have our limits all substituted in there. So this is what we're going to get. And notice how the cos of x cancels out. Now, this only happened because of our choice of u, because we picked sine x. So things will nicely cancel out. So we didn't have to worry about substituting cos x. I know maybe some of you have wondered, well, what about cos x? You've replaced everything else except for cos x. Well, it's because I knew it was going to cancel out eventually because of this substitution method. So now what I'm left with is the integral of u squared, which is just basically u to the power of 3 over 3 using the power method. And then all you're going to do is substitute your values in there, which are nicer values than the pi over 2, pi over 4. So then you end up with this value. Now, let's say you didn't want to change the limits. If you didn't want to change the limits, then you would end up with u. Let's say you would end up with, I'm going to write or. You were going to keep it as such, which is mathematically incorrect. But what you'd have to do then, if you don't want to change the limit, is bring back your original value. So you have u cubed, so you're going to write sine x cubed over 3. And this is from pi over 2 to pi over 4, and you're going to evaluate that again. So basically, you're back to this step. You're going to evaluate it, divide by 3, and so on, minus whatever you'll have to do. You're going to get the same answer. So if you want to avoid changing the limit, you're going to have to bring back the substitution in the end. So this is how you'd integrate with sine and cosine. Obviously, the questions will get more complex, but the best method you want to use for sine and cosine integration is by substitution. And remember to change everything, the limits, the dx, and so on when you're integrating.